Hello, welcome back. Let's take a look at a non-standard minimization problem. Before we get too far, I do see a typo on the third constraint right here. We should have plus 6x2, not 62x2. Okay, so plus 6x2 right here. Okay, so first we have a non-standard minimization, so we're going to have to write an equivalent standard maximum problem. So let's go ahead and do that. So we will maximize, and we're not going to use z, we'll use w, but w is going to be negative z. And that's because the minimum of a objective function will be equivalent to the maximum of the opposite objective function. So we're going to maximize w equaling negative 30x1 minus 15x2 minus 16x3. Subject to the following constraints. Now, if we look at the constraints that we've been given, the first constraint has the inequality pointing the wrong direction. So to correct that, we need to multiply the whole inequality by negative 1. So our first constraint will be negative 5x1 minus 3x2 minus 4x3 less than or equal to negative 45. Constraint number 2 is perfectly fine. The inequality is going the right direction, so that will remain unchanged. So we have 5x1 plus 6x2 plus 8x3 is less than or equal to 120. And now the last constraint is an equality. So if we go ahead and I'm going to call everything over here on the left, that's a. So what we have is that a is equal to 300. So this means that a has to be less than or equal to 300, and a must also be greater than or equal to 300. So the first inequality is the correct type of inequality, but the second one is pointing the wrong direction. So if we multiply that by negative 1, we'll have negative a is less than or equal to negative 300. And so these two sort of forms are going to give us our two inequalities from the third constraint. So the first one, a less than or equal to 300, that would be 20x1 plus 6x2 plus 14x3 less than or equal to 300. And now our final constraint will be negative 20x1 minus 6x2 minus 14x3 less than or equal to negative 300. And of course, we still have x1, x2, and x3 being greater than or equal to 0. Alright, so now that we have rewritten our problem as a standard maximum, we can go ahead and set up our initial tableau. Now you may notice that we have some negative constants, and so we're going to have to deal with those with phase 1 of the simplex method. So let's go ahead and get our tableau set up right now. Okay, so here's our initial tableau. And so since we have negative terms in our constants column, we're going to need to do the simplex method in two phases. The first phase will pivot we will have to pivot back into the feasible region. Right now, notice that if we try to find a basic feasible solution, slack variable 1 and slack variable 4 would have negative values. But we can't have negative values for our slack variables. Everything must be positive or non-negative. So we have to get back into the feasible region. And that's what phase 1 does. So right now we're going to go ahead and do phase 1 before we can apply the simplex method as we've been doing before. Now the way this is going to work, you pick any negative number from the constants column. I chose to use, and that's going to determine your pivot row. So I chose to use the negative 45, and then you pick any negative from that row, and that will be your pivot element. So I could have chose negative 5, negative 3, or negative 4. I chose to do negative 5 because it will divide 45 evenly. Okay. Now, there's no correct choice as long as you choose a negative number that's in the pivot row. We also could have chose to use row 4, and we could have used any pivot negative 20, negative 6, or negative 14 as the pivot element. Without actually doing the simplex method from there, you can't really tell which one's going to be fastest or simplest. So you just sort of have to try to, choose something that's easy to work with. So that's why I chose the negative 5, because it would divide negative 45 evenly. Okay, so we're going to pivot on this negative 5. So we're pivoting on the negative 5. And so that means I'm going to need negative 1 over 5 times row 1 into row 1. Now I'm going to just write the tableau between each step, but you can see the work for the tableau. This will all be available up on Blackboard, so you can sort of follow along as we go through from there. Okay, so I will go ahead and write the tableau for us now. Alright, after dividing row 1 by 5, we end up with the following tableau. And so we are pivoting on the 1 that is in the 1, 1 position. So if we pivot, we will need negative 5 row 1 plus row 2 into row 2. Let's see, we'll do negative 20 row 1 plus row 3 into row 3. Positive 20 row 1 plus row 4 into row 4, and finally we'll have negative 30 row 1 plus row 5 into row 5. Okay, after pivoting, this is the tableau that we end up with. So now we have to check, are there any negative values in the constants column? If there are any negatives in the constants column, then we have to repeat phase 1 again. You don't have to worry about the negative in the W entry, so in the bottom row, because it's okay to have a negative output for your objective function. So when I say the constants column, I'm only referring to the constants that are tied on to the constraints. We do have a negative in the bottom, in row 4, and so now we check, is there also a negative in the row? And there is, so we're going to pivot on the negative 4. So we will go ahead and do negative 1 over 4 times row 4, and this goes into row 4 in order to make that negative 4 a 1, and then we will pivot from there. So let's go ahead and see what that looks like if we divide row 4 by negative 4. So after dividing row 4 by 4, we end up with the following matrix. And remember, we are pivoting on the 1 that is in row 4. Okay, so we need to continue to pivot here, so we will do a 1/5 row 4 plus row 1, and this goes into row 1. We will do a negative 4 row 4 plus row 2 into row 2. Oh, sorry, just a negative row 4, not a negative 4. Just a negative, because we just have a 1 right here. Okay. Let's see, we're going to need a negative 4 row 4 plus row 3, and this goes into row 3. And last but not least, we have a negative 6 row 4 plus row 5, and this goes into row 5. Okay, so let's go ahead and pivot, and we'll see what we end up with. So now that we've pivoted, we see that there are no more negatives in the constants column, and so this tells us that we are done with phase 1. So now we will go ahead and begin phase 2. Now phase 2 is just our standard simplex method, exactly what we've been doing, for the last week. So that means that we look at the most negative term from the last row, and in this case that would be a negative 5, and then we take the ratio of the constant, so the 15, and we divide it by 7/10, and we see what the ratio is, and we do that for each row. So for the first row we would get 21 over 42, the second row is a 9, the third row is 0 divided by 0, so we shouldn't pick that row because we have division by 0. Row 4 gives us a negative 80. So the smallest positive number is the 9, so our pivot element should be the 9/2. So we're going to go ahead and pivot on the 9/2. So we will take 2 over 9 times row 2 and put this into row 2 in order to make that element a 1. So let's go ahead and do that. Okay, so we are pivoting on the second one that was in row 2, and so now we will need negative 7 over 10 row 2 plus row 1. This goes into row 1. We don't need anything for row 3 because we already have a 0. Row 4, we need 1/2 row 2 plus row 4 into row 4. And finally, we need 5 times row 2 plus row 5 goes into row 5. So let's go ahead and do those operations and we'll see what tableau we end up with. Alright, so after pivoting, we see that the last row no longer has any negative terms, except for the constant at the very end, which is acceptable. So this tells us that we are done with the simplex method. So this is our final tableau. Alright, so now that we have the final tableau, we can go ahead and interpret our results. So remember, the first column is x1, x2, x3, and then we had slack 1, slack 2, slack 3, slack 4, and our final column represents w, not z, right? Not the same z that we started with. This is the opposite of z. So we can say that w has a maximum value of negative 405 at the point, and let's see, x1 would be 87 over 10, x2 would be 0 because it's not a unit column, x3 is a unit column, so x3 would be 9. Now if we just leave our answer at this point, we haven't technically answered the question that we were asked. The question was, what is the minimum value of z? So now we take our answer and convert it to a result in terms of z. So we know then that z, which is negative w, so z has a minimum value of negative 405, or simply 405, at the same point. So at 87 over 10, 0, and 9. So our final answer would be the statement about the minimum value of z. Okay, so this takes a bit of work, right, because you have to go through phase 1 and phase 2. But when you're actually applying the simplex method, it's exactly the same as what we've done before. So phase 2 is what we have done in the past for a standard maximization. The only thing that's different is if you have mixed constraints, then you have to pivot into the feasible region, and that's what phase 1 is doing. The other thing I want to point out is just make sure that when you have mixed constraints, make sure that every equal sign becomes 2 inequalities, right? Not just 1. I think that's probably one of the most common things that's forgotten. We always want the inequalities to be less than or equal to, and so an equal sign will become 2 inequalities in that case. The other thing I want to point out is the solution from the tableau is the maximum value of z, right? And so of w, and so when we want z, it's always going to be the opposite of the number that's in the tableau. So if you got, say 106 in the tableau, then your minimum value for z would be negative 106. So just make sure you pay attention to the sign and make sure to switch it when you go back to z. All right, that's all for now.